Sure, industrial automation is all fun and games when you're using your cute little toy development board in the safety of your lab bench. You can feed in some signals and watch the outputs change, and it's really cool. But then, what happens when you need to use that design to drive some real-world actuators? You know, the kind of stuff that might be hooked up to big, expensive, dangerous machinery and subject to nasty stuff like extreme temperatures, moisture, and even lightning. That's when we need some professional help with our analog output capabilities. Hi, I'm Amelia Dalton, host of Chalk Talk. Designing your industrial-grade analog output using simple, discrete components is easy and fun. If you're an experienced analog ninja with lots of time and budget on your hands and can afford a few fails on your first couple of tries. But most of the world would like a little help doing it right, and getting it done quickly. My guest today is Bill Leilmeister from Maxim Integrated, and we're going to talk about how you can get your actuators rolling safely and surely with a really cool and robust analog output solution. Before we get started, don't forget to click that link. There you can download a free tech packet that includes a lot more information about Maxim Integrated's analog output solutions. Thank you so much for joining me again, Bill.
It'll be fun, I'm sure.
Okay, so I'm working on my industrial automation application. I've got all my algorithms down, but now it's time to actually drive something in the real world. So I need some analog signals to drive my actuators. Is that what we're talking about today?
Exactly what we're talking about. Anytime we have to interface to the real world, we have an analog world. So if you're doing industrial in a factory, you're doing building and taking care of HVAC, whatever it is you're doing, you have to, in the end, move something.
Right.
And that's what we're going to do. And
Excellent.
so on the left side of the drawing is the analog input. That's what we talked about last time.
Yeah.
Then comes the controller, and that's where your algorithms are going to live.
Excellent.
And now we have to get out to the outside world. The first thing we want to do is isolate it for data. And that makes sure that if there's a short of a high voltage wire on a data line, it doesn't ripple through and take out the whole system. It just takes out a small part of it.
Good.
And then in order to match that, we have to have isolated power. And then a voltage reference gives you the peak-to-peak voltage precisely with temperature and accuracy for the DAC. And then the output of the DAC goes into a super amplifier.
Okay.
And this amplifier is designed to be really linear and have some error correction or an error detection information comes back to the controller unit.
All right, so I know some people who are analog experts who can build this whole thing with discrete components and barbed wire, but I'm not that kind of analog expert. We're not going down that path, are we, Bill?
No, and I prefer baling wire to barbed wire. It doesn't hurt quite as bad. But we look on the right side of the screen, we'll see that there's an all-discrete implementation, which gives you the absolute most flexibility, but you have to have the most knowledge.
Yeah.
On the left side, you can have an integrated system that does one job, because you can't have something that does everything, right?
Right.
And then you have in between where you have the hard parts integrated, but you can change them around a little bit and have some flexibility.
That sounds good to me. So how do other people handle this?
Well, we have some really good competitors, and the good news about that is that makes us work harder too. Okay, but they have several boards, and some are to do some of the things that we're doing in this particular board, and others don't. And some are expensive and need a lot of test equipment, and others just aren't for sale.
Yeah, not for sale. Pretty clear at the bottom of that slide there. Okay. All right, Bill, now I see what the competitors are doing, but show me what Maxim's solution looks like. I want to convert some bits to analog and find out exactly how I did.
Okay, so we come out of the laptop USB and we convert that to SPI.
Oh, yeah.
And so now we're talking to the DAC and to the output configuration of the amplifiers. And then we go out with a couple of test leads to A to D board that allows us to convert back and actually looks like an oscilloscope on the screen of the laptop.
Yeah.
And so you can wiggle the bits on the laptop around the left side and look at them coming back on the right side. And all the stuff on the bottom of the slide is stuff that's in the kit.
Okay, cool. All right, Bill, down on that lower corner, I see a GUI there. Now, what does that look like?
Well, there's actually two GUIs.
Okay.
The left-hand side of the screen is the GUI for the analog reference board, and this is the one that has the output conditioners in it.
Okay.
And one of the tricks in those output conditioners is monitoring errors that are happening out down the wire from it. So in voltage mode, it's looking to see, did the wire get shorted?
Right.
In current mode, it's looking to see, did the wire open? And that's important because in the vibrations in a factory or something, the wires get vibrated and pretty soon they open momentarily. Well, we latch that.
Yeah.
And so all of a sudden you say, hey, something happened. Now we can pull an interrupt and the microprocessor can go look at it and figure out what happened. And if it happens a couple times, you say, well, I better send a maintenance guy.
Right.
And then the other thing that happens when you power this up, you notice that there's an error called brownout. When you power it up, guess what happens? The power comes up slowly. It starts monitoring and says, oh, I'm in brownout. And finally, when the power gets all the way up, right, it's latched it because you want to know, did power suddenly drop and come back, right?
Right.
Because that could be a problem. And so we make sure that we latch and fire an interrupt for that one too. So power up the board. It's going to say there's a brownout. You push the button that says reset, and it will go away and continue monitoring.
Great. So, Bill, let's talk more about this analog output module.
Well, the analog is a real issue when it comes to doing things because so many people have lots of information about computers and experience with digital, but not much with analog. So it's getting to be an old-timer thing. The guys are getting gray, and now what do you do? Well, in this case, we talked about data isolation, and we have isolators from 200 volts to 5 kV.
Okay.
And let's go down to the bottom below the DAC is the voltage reference, and its job is to be stable.
Okay.
With temperature and with initial accuracy, because if that drifts around, then the output of the DAC is going to drift around. Now, why would we use a 16-bit DAC? Isn't that kind of overkill?
Yeah.
It is overkill. But the reason is that in analog, every time you go through another stage, something degrades. Signal noise, linearity, something, right?
Right.
And so you start off with a lot more precision than you need. So by the time you get to the place where you actually need it, then it works, right?
Okay. That makes sense.
And so in reality, this board is going to be about 14.7 effective number of bits.
Okay.
And this is not all the system, right? I mean, so that's just this little piece of it.
Yeah.
So now let's go to the output amplifier or signal conditioners. And this is a fancy op amp.
Okay.
And it's powered strangely in order to keep the linearity. The first part of it is powered from a higher voltage than is the output stage. That way, when you have, in the world of IC designers, they think funny.
Yeah.
Okay. When we think about designing discrete devices, we think much different, where they'll have current mirrors, they'll make one voltage and replicate it 40 times, and their transistor is not one transistor, it's a whole bunch in parallel, right? So that they can control the exact characteristics they want. And so in that first part of that amplifier, all the current sources and things are all tied to higher voltages so that you never run into the end of the power supply. Back in the old days, they had 15-volt supplies on op amps.
Yeah.
Then they came out with what's so-called rail-to-rail ones. Well, they're not really. Okay. If you take a transistor and just lay it on the table without a power supply, it doesn't have much gain.
Right.
And when you run the amplifier into the ground or into the power supply, it stops having gain too. So it's not really. I mean, it's like if you don't draw any power in the output, you can almost get to the rail.
Right.
But that doesn't work that way. And so in order to prevent that, that's why we power the output with this lower voltage. So let me illustrate what happens when, and you also want to slew rate limit the output. You don't want to go from between two numbers really quickly because it causes some other problems. I'll explain that in a minute. But I know the audience can't see it, but we have these nice condenser microphones in front of us with a nice pop screen.
Yes.
The pop screen is slew rate limiting. Now, if I take the pop screen and move it out of the way, and you can hear the pop, if I blow into the microphone, I just crush it into the power supply. So I clipped it, right? And so as a result, that means that during that time, there's no signal other than that can get through. And so the same thing happens with the output here. If, let's say, for instance, you have a 4 to 20 milliamp output loop and you have a heart signal, which is a higher frequency. It's a Bell 202 modem on top of it. If you punch it into the power supply or in the ground, none of that gets through it. It gets lost. So you have to stay under 10 hertz with your signal. And so now you got a 16-bit DAC. So instead of going from one number to one other number, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, slowly, to say under 10 hertz, and that way you don't have holes punched into the heart signal. And if you want more information about that, go to Heart Foundation. So this is the situation of the board. Now, there's some other things that aren't shown here, but we have another application notice called AN6008.
Okay.
And it's protection, how much is enough. And it gives you everything from diodes to neon lights to protect the output from high voltages and things coming in. In the worst case situation where you have lightning hitting in your oil refinery or something, right, you don't use 4 to 20 milliamps. You convert it to 3 to 15 psi air,
right,
and you drive the valves out there where there's lightning with compressed air.
Yeah, Mother Nature always wins.
Yeah, and that's not a place where you even want to go look during a lightning storm.
No. All right, Bill, so how do we power this stuff?
Carefully. Okay, the magic here is the transformer.
Okay.
That's the isolation device. And so we take a DC voltage, and the flyback controller chops that and makes it into an AC voltage to go across the transformer.
Okay.
Then we rectify it and regulate it with the LDO, and then eventually with a voltage reference for the really precise stack part of the situation. So it's a way to keep you isolated from the grounds and voltages out there.
Now, back in the beginning, you mentioned that there were some advantages of hybrid over discrete or monolithic solutions. Now, how does that apply here?
In this case, we've put together 4 channels.
Okay.
And that's because the DAC we chose has 4 channels.
Mm-hmm.
Put away, you can make it 1 channel if you wanted to, but most people want to do 4, 8, 12. And
Sure.
so it makes it convenient to do it in groups like that. And that's what this shows here, is that flexibility. If you had it all integrated together, it'd make it more difficult to do that.
That makes sense. So how would you summarize this? What does it buy me?
It buys you integration in the hard part.
Okay.
That output amplifier is a tough thing to design and get it linear.
Yeah.
And so by doing that, we're able to handle anything between plus and minus 10 volts and plus or minus 24 milliamps.
Okay.
And be linear in the whole thing. And then notice in the middle of the slide, there's a 12-bit DAC. And that gives you the opportunity to say, well, I really need 6 or 7 bits, right?
Yeah.
Or whatever. So and I'm not going to go to 16, but I'll go to 12 and then, let it go down from that point. So it's looking at the application, figuring out what the end result is you want, and then figuring out the best, fastest way to design that.
Gotcha. Okay. What kind of performance can we really expect here?
Well, if we look at the output, we'll see that it's the 16-bit DAC is actually putting out 14.7 bits effective resolution.
Yeah.
And this gives you an idea of the linearity. And you look at it and you say to yourself, wow, that's bumpy. Now look at the scale on the left-hand side and you realize all of a sudden this is a tiny amount. This is less than 0.1% kind of thing.
Yeah.
So if that's still too much, you could go to an 18-bit DAC, or you could go and calibrate this and remove those. So this is the total unadjusted error.
Okay. So, Bill, why don't you give me a recap of your main points? I'd sure appreciate that.
What we're trying to show here is a quick demo, something that you can take out of the box. It takes longer to load the software than it does to actually set the mechanics up of the thing, right?
Right.
And now you can plug the boards in, you can play with them, and you could actually put this into your prototype and actually use it before your software guys have gotten time to do the code.
I love it. Okay. Well, I think that's all I have time for today. Thank you so much for joining me, Bill. It's always a pleasure speaking with you.
Thanks. It's been fun.
Before we go, don't forget to click that link. There you can download a free tech packet that includes a whole bunch more information about Maxim Integrated's analog output solutions. For Chalk Talks, I'm Amelia Dalton. For more Chalk Talks, check out the EE Journal YouTube channel or the on-demand section of eejournal.com.